Okay, part G. We have this for f1 of x. This is show the limit of f1 of x as x approaches 1. So the limit as x approaches 1 of this thing here, this nx to the n plus 2 minus n plus 1 x to the n plus 1 plus x over x minus 1 squared. Now essentially, as x approaches 1, essentially what we want to do is sub in 1 into this. So this is equal to, if I sub in 1 here, I get n, because 1, I'm subbing 1 in for x. 1 to the power of anything is 1, so I'm just left with n, minus n plus 1 times 1 again, so because 1 to the power of anything is 1, and plus 1 because x is 1. And then the numerator is 1 minus 1 squared. Now, n minus 1 plus 1 is 0, and 1 minus 1 squared is 0. Hence, this is in indeterminate form. So this is indeterminate form. Okay, that's GI. He says, so that was only 1 mark. For 2 marks, hence by applying L'Hopital's rule, show that the limit of this is equal to this, right? So we need to get the limit of this using L'Hopital's rule. I like this question, guys, because, well, I know what to do. We just need to differentiate the top and differentiate the bottom and see what happens. So we're going to say the limit as x approaches 1 of this, let me just copy this, guys. I don't want to have to write that whole thing again, right? So this, the limit of this is equal to the limit as n approaches 1 of the derivative of the top times the derivative of the bottom, right? Let's differentiate the top. Same as basic differentiation, guys. Multiply by the power, subtract 1 from the power. 2 minus 1 is 1. Minus, multiply by the power, n plus 1 times n plus 1, subtract 1 from the power, x to the n. And here, the derivative of x is just 1. Differentiate the bottom. Multiply by 2, subtract 1 from the power, done. Chain rule, times 1, just the same thing. Okay, then we sub in 1. Now if I sub in 1 here, I'm going to get, if I sub in 1 here, I'm going to get n plus 2 times, I'm going to get n plus 2 times n times 1 minus m plus 1 times n plus 1 plus 1 over 0, and this is equal to n squared plus 2n minus n squared plus 2n minus 1 plus 1. If you multiply that out, guys, I did that obviously very quickly in my head, but if you were to multiply that out, you get 0. So this is 0 over 0, which means we have to differentiate again. So I'm just going to write L'Hopital's rule again. L'Hopital again, just to show the examiner you know what you're doing. Okay, so it's the limit again as n approaches 1. Now we're differentiating this guy, so same thing, we're going to multiply by the power. Multiply by n plus 1 times n plus 2 times n, x to the power of n, because we subtract 1 from the power. Here, multiply by n, n plus 1 times n plus 1. I'm multiplying by this power, and then I subtract 1 from this power, so this becomes x to the n minus 1. And this guy disappears because the derivative of 1 is 0. And this is all over the derivative of 2x minus 1. Well, that's just 2. because it's like 2x minus 2 if you multiplied it out. So you get this. Okay, now I'm going to sub in 1. Let me move down a bit. Okay, I'm going to sub 1 into this. So I get n plus 1 times n plus 2 times n times 1. That just disappears. Minus n times n plus 1 times n plus 1 times 1. All divided by 2. Okay, best thing to do here, guys, you could multiply everything out, but don't. Factorize. I can take out the n, and I can take out an n plus 1. And what's left is an n plus 2 minus an n plus 1. Don't forget your bracket. And this is all divided by 2. And now we're left with n times n plus 1 times n plus 2 minus n plus 1, or minus n minus 1 is just 1. So this whole thing becomes 1. Let me just show that. So that's times 1 all over 2, which equals a half times n plus 1, which is what we wanted. So that is proved, our QED. Okay, that's question 1, guys. Definitely not an easy start to paper 3. Hopefully question 2 is better.